Hi, in this video, we will learn how to build a neural network completely from scratch. We will start with the mathematical foundation for this neural network, and after that, we'll be coding it starting from the very basics. We will not be using TensorFlow, we will not be using Pytorch, we will only use NumPy so that we can perform certain mathematical operations, and we'll be using pure mathematics. So this video is very suited for a complete beginner, and even if you have implemented neural networks using existing packages, which you can do in maybe a few lines of code, if you go through this exercise, you will appreciate a lot about the inner workings of these deep neural networks. My name is Dr. Sridhar Panat, and I'm a PhD from Massachusetts Institute of Technology. So without further ado, let's get into the video. The problem that we'll be looking at today is classifying MNIST images. This is very famous. I'm sure you have heard of this if you have played a little bit with machine learning. Basically, these are a set of handwritten digits from 0 to 9. So there are 10 digits, right, from 0 to 9. So this is like a 10 class classification. The task is to build a neural network which can be trained on a collection of these images so that if a new handwritten digit is presented to this neural network, it can make an accurate prediction. You can see that some of the images are very difficult to predict. For example, this one over here, it's very hard to say whether this is like a 7 or something else. And there are many such images in this particular data set. So we'll be using this MNIST dataset, and this will be a 10 class classification problem. Every single image is a 28 by 28 pixel image. So totally, there are 784 pixels in every single image. So it's highly pixelated. So this is the individual data set that we will be training the neural network on. A single data point consists of a single image, these many pixels, and the pixel values range from 0 to 255. 0 means that pixel is completely black. 255 means it's completely white. And if the value is somewhere in between, then it's like a grayscale. It can go from fully white to fully black. So this is a typical, this is how the typical MNIST image will look like. And now if you represent the entire data set, let's see how to do that using matrices. The training data set is obviously a collection of images, right? So the original MNIST data set has, I think, 60,000 or something so images. So today we'll be using a subset of that for training. So the training data set will consist of tens of thousands of images, which are very similar to this above image. So this is an image of handwritten digit 3, but the training data set will consist of images for corresponding to all digits from 0 to 9, and there will be tens of thousands of them, which means every class, basically image corresponding to digit 0 or digit 1, all of them will have close to 1,000 or 1,000 plus images in the data set. So how do we represent the training data as one single variable? So here, what we have written is the training data set X, the variable name corresponding to the training input data is X, is represented as a matrix, in fact, as a transpose of a matrix. That's why there is this T here. And every row, what is shown here, is one image. So similarly, if you have M such images in the training data set, M can be 20,000, whatever it is. It's a high number. We will see how much exactly this number is once we download the data set and once we are starting to code. But each image is represented by a row in this particular matrix. And of course, we are taking transpose. I'll come to that. And then this will be like before taking the transpose, this will be M by N matrix. After taking transpose, it will become N by M. So every row, currently it's an image, and there are M such images. And every row, in this case, has a length of 784. But after we take the transpose, every column will be of size 784, and there will be M such columns. Why? Because there are M such images in the training data set. So this will be an N by M matrix, where in this case, N equal to 784 times M can be 20,000, 40,000, depending on the exact size of a training data set. So this is the input data that will go into the neural network for training the neural network. And this will be represented in the format of a matrix. And what will be the value inside this matrix? The value will be the value of pixels. So this whole column corresponds to 784, the value of 784 pixels of one single image. So each column corresponds to one image in the training data. All right. Now let's come to the neural network architecture. The neural network consists of input and two hidden layers and output. So in the input layer, we are giving one image at a time, let's say, and that means we are providing the values of 784 pixels because it's 28 by 28 image. So the input has 784 nodes. So these are called nodes. And these nodes are fully connected with all the other nodes in the next layer. So this is like a fully connected neural network where every single node is connected to every single other node in the next layer and the layer before. So every single node in the input layer connects to every single node in the hidden layer 1. So this is the hidden layer 1 and this is the hidden layer 2, and 0 means it's the input layer. So that is how we are indexing. Now, how many nodes are there in the hidden layers? There are 2 hidden layers. We'll have 10 nodes in the first hidden layer and 10 nodes in the second hidden layer. And finally, the output layer makes a prediction. We will see the exact format of this prediction very soon. But basically, the input is one image of 784 values, pixel values. Then we have 10 in the hidden layers, both of them, 10 nodes, and then the output layer. Why did we choose 10? Because it is working really well. I have already implemented the code. It works really well. And we don't have to have a gigantic neural network for a relatively simple problem like this. Okay. Now, there are 2 steps which we'll be doing again and again and again and again, many times. The first step is forward propagation. Second step is backward propagation. Once we learn these 2, what exactly does this mathematically look like? We are good enough to start coding the neural network. So first, let us discuss forward propagation. In forward propagation, let us look at the dimensions of every single matrices that we are using. I already mentioned that the input image is represented by a 784 by 1 column, right? So it's like a vector of dimension 784. So the dimension of X, which is the input, which is an individual image, would be 784 by 1. Now, of course, we can also input, when we are writing functions in Python, we can input all the M images at once so that matrix multiplication can become much more efficient. In that case, this X can be 784 times M over here. Let me write it. Instead of 784 by 1. So this will also be 784 by M. But let's keep it 784 by 1 for now, assuming we are feeding one image at a time. So A0 means the output coming up from the 0th layer, which is the input layer. The output coming from the input layer is the input itself, which is the X, which is the image. Now let's look at what happens to this when it passes through the first hidden layer. The first hidden layer has bunch of weights and biases. So the way in which weights and bias act is like a linear function of the form y equal to mx plus c. So bias is this constant c that is getting added so that it acts like a intercept, and m is like a slope which makes the x scale to a certain degree, where x is the input that is coming into that layer. So A0 is the input that goes into the next layer, and then W times A plus B is the action that happens to this particular input, and that forms the immediate output that comes from the first hidden layer. But the final output that comes from the first hidden layer depends on what activation function we apply. But roughly, let's look at the dimension first before going into the next step. So the output from the first layer was from the 0th layer was 784 by 1. So obviously this will be 784 by 1. Now the input layer actually has 10 nodes, right? So some factor of 10 has to come in the weights, because there has to be weight associated with every single node. So it's fairly easy to understand that the dimension of this weight matrix should be 10 by 784. And then when this 10 by 784 gets multiplied with 784 by 1, it will become of dimension 10 by 1. So it is fairly easy to see that the bias matrix will be 10 by 1 because every node has one value as the bias, and we have 10 nodes in the first hidden layer, which is why it makes sense that this is 10 by 1, which means immediate output from the first hidden layer is 10 by 1. But before feeding this output into the next hidden layer, we perform something called as activation, and activation converts the linear output. So this is of linear form y equal to mx plus c. Activation function converts this into a non-linear form. If activation function was not present in a neural network, essentially it's like performing a linear regression. It's very, very difficult to learn complex non-linear patterns in the data for a neural network in the absence of activation function. So it's very, very important to have activation function. And what we will be using is something called as ReLU, rectified linear unit. And what ReLU does is, if the input to the ReLU is x, if the input is greater than 0, then the value of output of ReLU is that x itself, meaning that same value itself. So it will look like a line like this. But if the input is negative, then the ReLU converts that negative value into 0. So the ReLU of x is basically max of 0, x. So if this is x, then if this is x, this will be x. If this is X and negative, then the output is 0, right? But there are other activation functions also, like sigmoid. Sigmoid converts the input into a format like this, like an S-shaped curve, whose maximum value is 1 when X tends. So this is the equation for sigmoid. 1 by 1 plus e raised to minus x. When x tends to infinity, this tends to 1. When x tends to minus infinity, this tends to 0. So this is sigmoid of x. There are other functions also, activation functions like tan h, but we'll be sticking to ReLU in this particular example. Sigmoid is also very commonly used, so is tan h. So the final output that comes out of the first hidden layer is a of 1, similar to a of 0, which was the final output from the input layer. And that is nothing but activation function ReLU of Z1. Z1 is the immediate input which came out of the first hidden layer. Now this is fed into the next hidden layer. Next hidden layer also has set of weights and biases. So A of 1 is 10 by 1. And since there are 10 units in the second hidden layer, 10 nodes in the second hidden layer, it's fairly easy to see that this dimension should be 10. But this dimension also should be 10 because for multiplying W matrix with A matrix, this dimension should match with this and this should match. The second dimension of this and the first dimension of this should match. So this is also 10. So W matrix in the second hidden layer is 10 by 10 dimension. And B matrix, which is the bias in the second hidden layer, is 10 by 1 because there are 10 units. Every unit has one bias. So the output, immediate output coming out of this is 10 by 1. And then finally, we apply an activation to convert all of this into an output, which is softmax activation. Softmax is probably the most famous activation functions for creating probability distribution. So what it does is if you have certain numbers like y1, y2, etc. up to yn, applying softmax is like this. So you take e raised to y1 divided by sigma e raised to yi. So here in sigma e raised to yi, you can see that is common in the denominator for all the terms. So it is, this is not yn, this is also yi. So it will be e raised to y1 plus e raised to y2 plus etc. up to e raised to yn. So that will be the denominator commonly applied for all these. Numerator will be e raised to y1 for the first term, e raised to y2 for the second term, etc. e raised to yn for the last term. And you can see that when you add all these individual terms, the numerator will become sigma e raised to yi. Denominator is also sigma e raised to yi. And this is 1. So this is like a probability where sum of all probabilities added up is 1. And you can see the utility of softmax when you plug in some actual numbers. So imagine that the output y that comes out just before activation is applied in the output layer, it looks something like this. There are 10 values here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 numbers. And let's say the distribution of numbers is like this. When you apply softmax, you can see that smaller numbers like 2.3, 1.1, 0.2, etc. are completely suppressed. You can see that 1.1 becomes close to 0. 0.2 becomes close to 0. And the bigger numbers like 9.2, 8.1 are amplified. So 9.2 becomes 0.708. When I say amplified when you compare with 1, because the sum of probabilities are 1. So you can see that here softmax of y makes these numbers, which were on the left-hand side, into a probability distribution, where you can see that there is a 0.708% or 70.8% chance that this number, whatever this vector is representing, is the number 6. So now 6 becomes the prediction made by the neural network. Then what we have to do is compare this prediction with what the actual value corresponding to that image was, because an image as an input results in this kind of an output, and you have to compare whether the actual label associated with the image was same as this prediction or whether it was different, right? So that comparison we have to make. But this is the steps that go in one pass of the forward propagation. Now it's time to discuss backward propagation. The job of backward propagation is to help us optimize eventually the parameters involved in this neural network. The parameters involved are the weights and biases in this particular neural network architecture. We have a weight matrix in the first hidden layer because the input layer, which is layer 0, has no parameters. It is simply the input. We can't play with it. But layer 1 and layer 2 has certain parameters called weights and biases. The weight matrix corresponding to layer 1 has 10 by 784 as the dimension. Bias is 10 by 1. In the second layer, again, bias is 10 by 1, but the weight is 10 by 10. So we have these many weights and these many biases to optimize. So this is the whole idea of backpropagation. It is like, how can we change the values of weights and bias such that in the next round of forward propagation, we are making a better prediction? Because we made a prediction in the previous round. We saw that maybe the prediction is far away from the real, actual value of the image, actual label of the image. And then with that knowledge, how are we going to modify the original values of W1, B1, W2, and B2? And one thing which I want to mention here is that when we first start the neural network, when the very first forward propagation pass is done, we initialize W's and B's with random values. B can also be initialized with zeros, but we in this particular example, we'll be initializing it with random values. So starting with random values, which will make random predictions. Random prediction means the accuracy will be 0.1, because if you randomly say that if it's a 10 class classification, and if you randomly guess this to be an image to be 1 or an image to be that of 5 or 6, you have a 0.1% chance that you'll be, 0.1 probability that you'll be correct, or 10% chance that you'll be correct. So when we start with random values, when we implement the code, you will see that the accuracy is just 0.1. But then we will see that as we modify the values of weights and biases, these 4 matrices, we will increase the accuracy. So how do we do this? How do we make this modification? This is where we have to look at the gradients. So let's see what the gradients do. So just before going into the gradients, let's summarize all the things we discussed, right? So we have output coming from the input layer is the input itself. Then immediate output coming from the first layer, first hidden layer is Z1, which is WA plus B. It's like a linear function. Then we perform non-linear activation. In this case, it's ReLU. And ReLU performs max of that input, 0. Then in the second hidden layer, we perform again a linear multiplier like this, WA plus B. And then finally, we perform softmax activation to create probability distribution, right? So let's look at a sample prediction and let's compare it with an actual value. So actual value, let's say the actual image is that of a 3, something like this, 28 by 28 pixels. And this is that of a handwritten 3. How do we represent 3? We can represent 3 using something called as one-hot encoding. So here you have 0, 1, 2, 3, 4, 5 up to index 9. So at the index 0, it is the handwritten, it corresponds to 0 itself. So if you had an image of a 3, you have to put 1 at the second index, because this is 0th index, this is first index, second index up to 9th index. So if we have the image of a handwritten image of a 0, you put 1 in this 0th index and 0 in every other index. If you have 3, you put 1 in the second index and 0 in every other index. And this is called one-hot encoding. So if the actual image of this handwritten digit is that of a 3, it means label associated with this, because we have to know what this image corresponds to. So we'll have labels. So label is 3. And this 3, which is just a number, can be converted into a one-hot encoding in this format, right? Now we can compare this one-hot encoded label with the predicted label. And predicted label was of what format? This was a 10 by 1 matrix. The index corresponding to the highest value is the number corresponding to whatever this prediction is showing. So this is index 0, this is index 1, this is index 2, right? So if 0.7 is the highest value among all these numbers, all these 10 numbers, it means that index 2 has the highest value. And what is index 2 corresponding to? Index 2 corresponds to the number 3, like this. So here it was index 2, right? So then you can compare this y and y cap, and you can define a loss. And the whole goal of the backpropagation is to minimize this loss by optimizing the weights and biases. So how do we do that? Before coming to this gradients, let me show you the way we modify the weights and biases. So the weight 1 is modified such that the previous value of weight 1 minus alpha times some change that we bring to weight 1. So we impose this new value to the weight 1 variable, and alpha is the learning rate. Similarly, we will be changing the weight in the second layer and bias in the second hidden layer. Now, how do we calculate this? Because we know this, we start with random values. We start with random values. This is also random. This is also random. Alpha is something that we fix, because we'll say that alpha, the learning rate equal to 0.1 or 0.01, something that we are comfortable with. But how do we calculate DW1, DB1, DW2, DB2, etc.? That's what we are going to see now. Now, before calculating the gradients, I have copy pasted the equation for the first layer, first hidden layer, second hidden layer, and the final output layer over here, so that you can very easily compare the gradient with respect to the equation. We can also try to derive it, but I won't be spending too much time in the derivation because I would rather spend that time in coding. So over here, what we are trying to do is like calculate the rate of change of loss with respect to DW1, rate of change of loss with respect to DW2, rate of change of loss with respect to D bias in the first layer, and rate of change of loss with respect to bias in the second layer. So finally, this is what we want. And loss is actually depending on all these things, right? So the final loss will depend on weight in the first layer, bias in the first layer, weight and bias in the second layer. So now let's see how do we calculate, for example, starting from the second layer, how do we calculate D loss by dW2? So D loss by dW2, or rather the better way to do that is dou loss by dou W2, which is the partial derivative dou W2. And here loss is cross entropy loss, which is minus sigma I equal to 1 to n yi ln yi cap. So here yi is the value corresponding to one particular label. So in one hot encoding, if a number is 3, all yi's will be 0 except for that in the index 2. And yi cap is the prediction that is made. So ultimately, this will boil down to minus yi ln yi cap, where this is the actual label and this is the predicted probability for it to be that label. Anyways, so dou L by dou W2 equal to dou L by dou A2 times, actually not A square, let me write it as subscript, times dou A2 divided by dou Z2 times dou Z2 divided by dou W2. Sorry, dou Z2 divided by dou W2. Now, it is very tricky to calculate the derivative of loss when softmax function is involved. But the final format of this will be a very simple one. It is simply of this form, the prediction minus actual value. So this will be of the form y cap minus y. Finally, this will boil down to that. And dou Z2 by dou W2, you can see that it is nothing but A1, but you will have to take a transpose. Only then the matrix dimensions will match. So finally, the change which you are adding here, this one, alpha times, if you look at the W2, it is the previous value of W2 minus alpha times the change you are bringing. And this is nothing but dou L by dou W2, which is this guy, dou L by dou W2. And this will be equal to, what is the prediction? Prediction is A2 minus y. Y is the one hot encoded label times A1 transpose. And that is what is written here. A2 minus over here, dW2 is A2 minus y times A1 transpose. But you will also see that there is a 1 by m here. The reason why we have 1 by m here is when we are actually writing the code, we are not going to pass every image. If we have, let's say, 20,000 images in the training data set, we are not going to pass in the first iteration one image and then the next image and then the next image. We'll pass all the 20,000 images so that we can make the calculation much more efficient. So the weights has to be changed because the first image will produce some kind of loss. Second image will produce some other kind of loss. Third image will produce some other kind of loss. And the 20,000th image will produce another kind of loss. And we are taking the mean of all of that. And how many images do we have? We have m number of images. Each image had n pixels. 784 was the value of n. M will be a big number depending on the size of the training data. So that's why this 1 by m factor is there. And you will see that this 1 by m factor is coming in the updation of weights. Here you will see the 1 by m in the bias. So this is the second layer weight, second layer bias, first layer weight, and first layer bias. And everywhere you will see this 1 by m. And in the bias, we'll also be doing this. You will notice that there is a sigma dz1. Now, similar to how we calculated dW2, which was rate of change of loss with respect to weights in the second layer, the rate of change of loss with respect to bias in the second layer will not have this A term because A was a coefficient with the W. But when we do dz by dz2 by dB2, it's equal to 1. Whereas when we did dz2 by dW2, it was A1 transpose. So only difference between dW2 and dB2 is the absence of this term. So you can see that here, the A1 transpose term is absent. Now, similarly, we can also calculate, we can backpropagate and we can calculate rate of change of loss with respect to weights in the first layer and rate of change of loss with respect to weight, bias in the first layer. One thing to notice here, there is a ReLU prime that is coming because when we are calculating dou loss with respect to dou W1, this is equal to dou loss with respect to dou A2 times dou A2 with respect to dou Z2 times dou Z2 with respect to dou A1 times dou A1 with respect to uh, dou Z1 times dou Z1 with respect to dou W1. So this part we calculated it to be A2 minus Y, right? Then dou Z2 by dou A1 was W2. Then there will be a transpose coming. Then dou A1 by dou Z1 would be ReLU prime. This is the derivative of ReLU prime of Z1. And then finally, dou Z1 by dou W1 will be a not, I think a transpose will also come. So finally, when you put all of this together, this will be, I think, A2 minus Y. Although I'm going fast in this derivation, I'll be sharing this notebook with you so that you can, at your leisure, go through this. But I just wanted to show you this. Times W2 transpose, and then we'll have an element-wise multiplication with this ReLU prime of Z1 times A0 transpose, I hope. Let's see if that is what the case. W2 transpose, right. So this is over here. And there will be a 1 by m if we are passing multiple images at once instead of one image at a time. And you can add the 1 by m here because you are taking an average of losses that are caused by every single image. So 1 by m comes here. So that is this term. And then finally in dB1, this guy will be absent. In when we calculate rate of change of loss with respect to bias in first, this A0 will be absent. And then there will be a sigma added. So you will see that sigma here. And this A0 will be absent. A0 was present in the rate of change of loss with respect to weights in first layer, but in the rate of change of loss with respect to bias in the first layer, A0 term is absent. So this is in summary how to write the gradients. And now I think it's a very, very good time to start coding. But before coding, let's see what exactly are we doing, right? We start with random weights. So the very first step is random weights and biases. Then the first step of forward propagation. Then we see how much the gradient of loss with respect to weights and biases are. And that is the first step of backpropagation. Then we have a new sets of weights and biases after that. And then we again do forward propagation. Then we get a new output, new predicted output. And then we again compare this output with respect to the earlier one. And then we again do backward propagation, and then so on and so on. We can do this 500 times, 1000 times. The more number of times we do, the more the network will learn about the training data. So I think at this point, we have fairly, in the constraint of time, we have fairly well looked at the mathematical theory underlying neural network. And now let us start coding from scratch. So I'll be coding in Google Colab Notebook. You can use Jupyter Notebook, Kaggle Notebook, anything that makes you comfortable. So first, let us import the packages. So we'll be using NumPy, we'll be using Pandas, and we will be using matplotlib for plotting. So import NumPy as NP, import Pandas as PD, and from matplotlib, import pyplot as PLT. So this will help us plot the image, the 28 by 28 pixel image finally. So we can run this. This should have no issues. Now, next step is finding the dataset itself. So let's download the dataset and upload it into Google Drive. So, and then I'll show you how to connect the Google Drive so that you can directly import the data to this notebook. So you can download MNIST dataset in CSV format. So basically it won't be images. It will be rather pixel values of all the images in training dataset and all the images in test dataset put into one single CSV file. In fact, two separate CSV files, one for training and one for testing. So you can download it from here. I'll share the link in the description. But I will also share one more link in the description to this particular folder. This is the final downloaded format of the digit recognizer. So it has train.csv and test.csv. We won't be using the test.csv because we can split the train itself, this particular train itself, into training and validation. So what we will do is we will upload this particular folder called as digit recognizer into Google Drive, and then we can get access to this train and test.csv if needed from the Colab notebook itself. So let's see how to do that. So firstly, ensure that you have uploaded that particular folder, digit recognizer folder, somewhere on your Google Drive. And then we can use this piece of code to connect Google Colab and Google Drive. So from google.colab, import drive and drive.mount/content/drive. And when you run this, it will ask you permission to connect drive with Colab. And then you will have to log in or sign in into your Google account. So that's what I'm doing here. So just give this permission. This is completely fine. And once this step is done, the connection between your drive and Colab is successful. So once this finished running, the connection should be fine. It usually is much faster, maybe my internet speed. Okay, so this is finished. Now go to this, not sample data, go to this drive folder, my drive, open that. And here, once this loads, if you go down, there should be a folder named digit recognizer. Yeah, here is the digit recognizer. And in that, there is the test and train CSV file. There is also one more file here, which is not needed. I can just delete it. Oh, sorry, not download, delete. I just deleted that. Then we have test.csv and train.csv. We'll be primarily using train.csv. So next, what we are doing is getting the data. So data equal to from here. So click on these three dots and click copy path so that you have the path with you. And pd dot read csv. Oh, you see this this recommendation is coming automatically because I have Gemini here, and Gemini will automatically recommend to you. So I'll use it. So if you press tab, I'm using Mac, so I press tab so that recommendation is used. The only thing I have to change here is this is not data.csv, this is train.csv, and this is digit recognizer, the folder name. The rest of the things are fine. So this should read the data. All right, so that much is fine. Now we can display the first 5 rows of this data set, and we can see how the data looks like. So you see that these are the first 5 rows, and every row is one image, because the first column is label, which means the first row corresponds to image of a handwritten digit of 1. Second one, the label, you see the label column. For the second row, it is 0, which means this entire row, which I have highlighted, corresponds to pixel values of a handwritten digit of 0. And you can see that this starts from pixel 0 all the way till probably 7. It should be till 783, because there are 784 pixels, and indexing is starting from 0. So the first column is the label, and all the remaining columns are the values of pixels. And the number of rows will be equal to number of examples that we have. And here in the head, we are only printing 5 rows, 5 examples, but in reality, we have much more, right? So that is the printing of the head. Now, we don't want the data in this pandas data frame. We want it to be in the np.array form. So we can say data equal to np.array of data. So this will convert the data into np array. And okay, it has already suggested basically m comma n equal to data.shape. Let me remove this. I think this recommendation is coming probably because I have already implemented this in Colab. But m comma n equal to data.shape, because m is the number of examples, like how many images are present in my data. That is the number of rows, and that is m. N is the number of pixels in every single image, and that is the number of columns that we have. So actually, m comma n equal to data.shape. It should be n minus 1, because here label is also coming, but we'll see. And then data.shuffle, not data.shuffle. We should shuffle this. np.random.shuffle of data. So the reason why this shuffling is done is because what if the data set has certain order? What if all the data set corresponding to label 0 is coming in the initial part of the data set, and then the final part of the data set corresponds to images of handwritten digits 8 and 9. We don't want that. We are completely shuffling the rows, not the columns, because label should remain along with the corresponding row. So we are shuffling. And I think if we print m and n, we should get the m should be the number of examples, and n is equal to 785. So this is an issue because actually we have only 784 rows. I mean 784 pixels. So n should be 784, but it's showing 785, and that is because here this column is also there. Label column is also there. So we will separate it out. So now let us split into training data and validation data. So train data equal to data of, and we'll be taking data of 0 to, let's say, 80% of, yeah. So here what we are doing is we should take 80% of the data set as training data. So here 0.8 times m means we are taking 80% of whatever is the number m. And what is m? The total number of examples in the data set, and we are converting that into an integer. So 0 to, that means all those rows, 80% will be used for training, and validation data will be equal to data of probably this should not be like this. This should be the remaining ones, right? This till m, comma, all the columns. So this is validation data. Now here in the training data, there is labels and the inputs. Validation data also has labels and inputs. So we should have x train, y train, x val, and y val. Okay, so I have clicked tab to take the suggestion that Gemini gave me, but I'm not going to use it because I'm sure there will be mistakes. So x train should be all the rows in this particular one, but I should not take the first column. I should not take the 0th column. So all the rows means I have to put a colon here, and the columns should start counting from 1 instead of start counting from 0. So that is the x train, and 0th column is y train. And here what I'm going to do is, like, I should take a transpose, because I want this in the format where every column corresponds to one image. I don't want every row to be one image. So let me do that also. So validation data and train data, and after before running this, let me print xval dot shape. I'll print all of these. Then yval dot shape, x train dot shape, and y train dot shape. I want to print this, so let me run this and let's see what the shape look like. Yeah, so this looks fine. So training data set has 33,600 examples, and it's a 784, 30. So n equal to 784, m equal to 336 in the training, n equal to 784, and m equal to 8,400 in validation. And 8,400 comma means it's just a one-dimensional array. This is the labels corresponding to the 8,400 examples in validation, and this is the labels corresponding to 8,400 examples in training. All right, so far so good. Now another thing that is very important is scaling. So x train should be scaled by a common factor, which we will use as 255. So we are scaling all the image pixel values from, instead of being 0 to 255 being the maximum value, we want the maximum pixel value to be 1. So this is kind of normalizing the image pixel values, and x validation is equal to x val divided by 255. We don't want to scale the labels because labels are from 0 to 9. All right, so let's run this, and let's run this. Okay, now it's time to define certain functions. So we need to define a function for initializing parameters, which is initializing the weights and biases with random values. I'll fill something here, but let me just return for now. Then we need a function for forward propagation. Then, so also let me write return. Then we need a function for backward propagation. So it's already giving me automatically this, but we need backward propagation. We need a function for updating parameters. Let me delete these two. We'll write it when we need it. Not right now. Okay, so initializing parameters, what are we going to return after initializing? We will return W1, B1, W2, B2, right? these are the four things that we are going to return after initializing. And how are we going to initialize? So W1 and B1 should be random. So I'm using the suggestion that Gemini gave me, but basically let's look at the logic rather than blindly following this. So should be of same indentation. Yeah. So W1 equal to np.random.rand. So this will create an array of 10 by 784, because let's go back to our equation. So W1 was, where is our dimensions written? Yeah, so W1 was 10 by 784. So we are initializing a random numbers from 10 by 784 of range 0 to 1. And we subtract 0.5 such that the range will be from minus 0.5 to plus 0.5. Then W2 equal to np.random. So B1 should be 10 by 1 and B2 should be 10 by 1, because there are 10 nodes in both first hidden layer and second hidden layer. W2 should be 10 by 10 as written over here, right? So 10 by 10. So this is the W1, B1, W2, B2 initialization. Now in the forward propagation, what are the inputs that the function needs? We need W1, we need W2, actually W1, B1, let me put it in order. W2, B2. What else do we need? We will come to that. So firstly, let us calculate in forward propagation. The first thing that we do is A naught equal to X. Okay, so Z1 equal to W1 times A. W1 times A. So this is actually matrix multiplication. So W1 dot X train plus B1. So let me input an X here. And here instead of X train, it can be simply X plus B1. A1, this is not tan hyperbolic. This is actually ReLU of Z1. NP, actually, we have to define a function. So because Z1 equal to W1 times A, matrix multiplication plus bias, and then we apply ReLU to get A1. And so which means we have to define a ReLU function, ReLU of X or anything. This will be, we have to return something like max of np.max of x comma 0. Yeah. So this is ReLU of Z1. Then Z2 equal to W2 dot of A1, correct, plus B2. And then A2 equal to, this is softmax. So instead of putting it here, let me write a softmax function. Softmax, maybe calculator of some Z. This is what it is supposed to return. It should return np.exponent of not Z2, Z. I'm not sure if we have to define the axis. Let's try without that. Softmax calculator for Z is, if you remember this formula for softmax, it is over here. It is e raised to yi divided by sigma e raised to yi divided by sigma e raised to yi for any value of I. So that is what we are doing here. E raised to np dot e raised to z divided by sum of np dot e raised to z, and we are returning that as softmax. So what we will do here is softmax calculator of Z2. This is the final thing. And now what should the forward propagation output? Let us put all of these things, Z1, A1, Z2, A2. Let us output all of these four things. Fine. Now let's come to backward propagation. So in backward propagation, we are going to modify the values of weights and biases. So obviously, let's input W1, B1, W2, B2, right? And in the backward propagation, for calculating the gradients, let's look at what other parameters are there in the equation. So we need y. So we can put y here. Then we need A1, A2, Z1, A1, Z2, A2. We can input that. Y maybe we can put last. And what else do we need? I think, yeah, A naught means that it's the input. So X also we need. So X comma Y. Right. I guess, yeah, that's pretty much it. If we need anything, we can write it afterwards. Now let's write backward propagation. What are we trying to calculate? First of all, we want to calculate dz2, dw2, db2, dz1, dw1, db1, right? These many things we are going to calculate. And we also need a y in one hot encoded form. So one hot y equal to So, and maybe we'll have to define a function here, one hot converter. We can call the function name as one hot converter of y. And let's define a one hot converter. Define one hot converter of y. I just accepted what this guy Gemini was telling me, but let's go through it, right? I'm sure there are mistakes. So one hot converter of y is, firstly, what do we need? We have labels, and what would be the dimension of the labels? If we are passing only one image, the dimension of the label will be 10 by 1, because it will be, it will be just a number, but after one hot encoding, it will be 10 by 1. So we need 10 along the row, and if we have m examples, it should be 10 by 1. So here, y dot size is the size of the label, which is the number of images themselves. And y max in this case will be the max value in the y. It will be 9, and 9 plus 1, 10. So this value will be 10, and this value will be whatever is the size of number of labels. So if we are using training data, we know that number of labels is 33,600. So that will be this number. So we are creating a zeros matrix like this. And then what we are doing is, wherever is the index of the y coming, we are assigning those value to be 1. So one hot of np dot arrange of y dot size comma y equal to 1. And then we are taking a transpose. I'm not sure if this guy is needed. Let's see. We can play with this separately. So one hot encoder of y. Let me call this function over here, np dot array of, this is an array, let's say one hot encoding of 1, 2, 2, 4. So this should, yeah, let's say this is, okay, maybe there is a comma. Should not be broadcasted together. So maybe we should, actually, I should simply provide a column array. So how about this? 1, 2 prime dot t. Okay, so here what we did is, okay, one more thing is we should probably output the transpose, because we need only 2 columns. Okay, one more mistake is in the input. Here, originally in our one hot encoding input, we are having a one-dimensional array. Like this has only one dimension in the input, which is the y. So we have y as the labels. If we have 33,600 example images, we have that many labels. So we don't need this double bracket. We just need single bracket. And so now what we have is, yeah, now this is a proper one hot encoding. So one hot encoding corresponding to, so if I had a 0 also here, the first will have one more column, and the first column will have 1 at the first position, you see. And if I had a 3 somewhere in between, there'll be, the third column will be 0, 0, 0, 1, and the length will be, currently this is 3 by 3, right? This is like there are 3 columns and 3 rows, but now one more will be added because maximum value is now 3. Okay, so this function is doing exactly what we need. So all we have to do is take a transpose. Let me copy this one hot encoder, delete this and paste it here. Okay, so that's the only difference. So this will convert into one hot encoding. Now dz2 we have to calculate is a2 minus one hot y. And why is that? Because here we have the equation is a2 minus y is dz2. dw2 is 1 by m times a2 minus y, which is dz2, times a1 transpose. And this has to be like a matrix multiplication. So 1 by m times dz2, which is this guy, dot a1 transpose. And a1 transpose is nothing but whatever we are passing here. Okay, so dw2 will be that. Now db2 will not have this guy, will not have this guy that we had already discussed while discussing the theory. So this guy is absent in db2. Okay, now in dw2, let me go with what they are saying. dw2, no, this is wrong. So Gemini was wrong. Yeah, dw2 equal to 1 by m dz2 dot, and why is that? So here dw Wait. So I first calculated dz2, then I calculated dw2. This should be dw1, db1, dz1, db2 is already calculated. I don't need any of this. So let me just put what I need. So dw2 was calculated, db2 was also calculated. So let me delete this. I should not directly accept what Gemini is suggesting. So dw1 would be 1 by m times w2 dot transpose. Yeah, let me accept this. w2 dot transpose, that is correct, times a2 minus y is nothing but dz2. So that is correct. This part is correct. Times, I don't think this is correct. Times ReLU prime. And ReLU prime, how do we calculate? Actually, the order might be flipped. Let's see. So this multiplied by ReLU prime, which is element-wise multiplication. So this is fine. And ReLU prime is what? ReLU prime is nothing but if the value of ReLU is greater than 0, then ReLU prime is equal to 1, because ReLU of x is equal to x if x is greater than 0. So it's nothing but z1 greater than 0. This is basically the ReLU prime. We don't need to define a function, a separate function for this. Times, we have, actually this is not times, this should be matrix multiplication. Dot, we need a0 transpose. A0 is nothing but the input itself. So this is x dot t. It would have been easier if we wrote dz1 here. So dz1 maybe is better to write here. And dz1 is nothing but w2 transpose this guy, w2 transpose times dz2 matrix multiplication dot element-wise multiplication with ReLU. So this guy, fine. And then this is nothing but 1 by m times dz1. So 1 by m I can keep, and then dz1 I can replace all of this with dz1 basically, dot x transpose, because there is a0t. A0 is nothing but the output coming from the input layer, which is the input itself. Okay, so this is fine. dw1 and db1. Okay, let's look at db1. db1 is nothing but this guy, 1 by m times sigma dz1. So this will be 1 by m times np dot sum of not dw1. This should be dz1, right? Yeah. I hope everything is correct. If not, we will fix it later. Now, what are we outputting? We need to output dw1, db1, dw2, db2. I don't think we need dz1 and dz2, but let's keep it here for now. And if we don't need it, we'll delete it. dz1, dz2 also we are outputting. And in the update parameter, what were we going to do? We were going to say that w1 equal to w1 minus learning rate times, this is what we already wrote. Somehow Gemini is so smart that it knows what to suggest. And so the input should be w1 b1, w2 b2, dw1 dw2, then db1. Okay, sorry, I should put db1 here for consistency, then db2 and learning rate. So learning rate also I'll add here. So this should be the update parameters. And what should this return? This should return again w1, w2, w1, b1, w2, b2, which are the updated parameters. Now the final thing should be gradient descent. So let's say we define gradient descent. And what are the inputs going into gradient descent? We will have input x, output y, alpha, which is the learning rate, and number of iterations. Number of iterations is like epochs. So first, I mean, I have already got the suggestion from Gemini, which is w1, b1, w2, b2. The initial value should be depending on initialize parameter function, which we have already written over here. So initialize parameter should return w1, b1, w2, b2. So that is here. Once we have the values of w1, b1, w2, b2, we can calculate the first round of forward propagation. So Z1, A1, Z2, A2 equal to forward propagation of what? Of some inputs. And these are the inputs, right? And then we do backward propagation, dw1, dw2. Yeah, I don't think we need dz1 and dz2. We can ignore it. So dw1, db1, dw2, db2 equal to backward propagation of all these guys. Backward propagation of w1, b1, w2, b2, z1, a1, z2, a2, x, y. Okay, we have everything. This is backward propagation, and then update parameters automatically. I got the recommendation, so I selected it. So w1, b1, w2, b2 equal to update parameters function, and alpha is the learning rate, and these are the inputs. So we provide that. All right, this is also fine. Now, what should we print? Let's come to that in a moment. We can do something like, we have to iterate this a few number of times, right? So what we can do is we first initialize, then for I in range of iterations, because this is how we iterate it over all the number of iterations. And we don't initialize it in all the iterations. We initialize these parameters only once. That's why I put this outside the for loop. And in each iteration, we can print something. If I mod maybe 20 in once in every 20 iterations, we can print something. 20 equal to 0. Then print accuracy or iteration number is I, and print accuracy equal to this should be, we have to calculate accuracy. Okay, it's suggesting me some function. Okay, fine, get accuracy, and we have to return the weights and biases from the gradient descent. Fine. Now we don't have this function. We don't have, what is this? Get accuracy, get predictions. So now what we need is, the accuracy depends on the predictions made by the neural network with certain set of weights and biases, right? So what is the prediction made by neural network at this point? The prediction made by the neural network at this point is A2, because see, after forward propagation, A2 is the output of the final layer. Where is that? Where is our neural network picture? Yeah, here. So A2 is softmax of Z2. So A2 itself is the prediction after, is the softmax prediction. So now we need to get a prediction as a number from the softmax. So for that, we can define, I mean, we don't even need this, I guess, but maybe since that has been suggested, we can write a function, define get predictions of A2, and we should return maximum value, right? The index corresponding to maximum value. I think it's like np dot argmax of A2 comma 0, correct? And then get accuracy. I got recommendation from Gemini. This is basically, I should, if I have m number of examples, which is y dot size, for every example, I'm checking if the predictions is matching with the y or not. So np dot, so this looks correct to me. And then we are outputting w1, b1, w2, b2. Okay, I think this is fine. Now what we can do is w1, b1, w2, b2 equal to gradient descent of, we need input. What are the parameters going to gradient descent? X, Y, alpha iterations. So X is nothing but X train. Y is Y train. Alpha learning rate could be 0.1. Number of iterations could be, let's keep it at maybe 100 for now. I don't know if now we can run the code for the first time. I'm sure some error is there. I don't think this code will work just like that. Let's see. If it works, I will be very happy. Okay, something. Okay, interesting. It actually is working. Currently, there are no mistakes. So in the first iteration, okay, this is printing the accuracy. So in the first iteration, the output is out the accuracy of prediction in the training. First of all, this is not it's like in the training process, it's 0.1. And do you know what 0.1 means? It means you have a very, very bad model. The prediction accuracy is barely matching random guessing accuracy. And then as iteration becomes 20, 60, 80, etc., it's increasing. So at 80th iteration, after 100 iterations, I guess accuracy is close to 0.5, which is not bad for a 10 class classification. So maybe we can increase this to 1000 and let's see what the accuracy is. So instead of running for 100 iterations, let we run for 1000 iterations. If we reach like something like 0.9, 0.95 accuracy, we'll be very happy. And while this is running, we can also perform some kind of visualization. So we can make some predictions on testing images. So how do we make a prediction? We make a prediction using forward propagation. For making prediction, we don't need backward propagation. So if we were to make a prediction, Z1, Z1, A1, Z2, A2 equal to, maybe I can say test or validation, Z1 val, A1 val, Z2 val, A2 val equal to forward propagation of the weights and biases plus input. And input is nothing but we can put validation data set x val, I don't know if it is capital V or small v, I forgot, of and validation data set was having a dimension of x val was 784, 8400. So we need all of the all rows we need. So this comma, let's say the index 1 or index 0 is also fine, any random image. So once this finishes running, we can test whether, and then this is the prediction, right? A2 val is the prediction. So now from A2 val, oh, sorry. A2 val, why is A2 val the prediction? Because A2 is the final softmax output. So now how do we get the actual prediction from this? We have a function over here, get predictions of A2. So all we need to do is here call the get predictions for A2 instead of A2 val. Then this should output the actual prediction. And how do we know whether this image is corresponding to whatever this number says is? Then we can plot the image to see that. We can plot, or we can also simply print the label. That is also an option. So we could probably first print predicted label equal to this, and print actual label. Actual label would be y val of 0. Maybe I can say it validation val index equal to 0. Then I can use this val index here and here. Actual label should be this. I think this is correct. Okay, so once my 1000 iterations are done, we can run this piece to see if this particular image, this corresponds to an image, whether that is correct or not. And how do we can use np dot or image array equal to, we can reshape this dot reshape of, I think the syntax is correct, I'm not 100% sure. Image array equal to this reshaped, and then we have the plot, import by plot as plt dot is it imshow? Let's see, plt dot imshow of color map. We can do it. Okay, fine. Color map is fine. Then plt dot show image array. Okay, so here the final accuracy is 0.86. Very good. Let me not print this image for now. Let's just run and see if this is working. Actual label, too many indices. Where is this issue coming? But 2 were indexed. Oh, okay. So it's because I just need 1 index. Predicted label is get predictions of A2 val. Get predictions of A2 val is return np.argmax of I'm not sure exactly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think the problem that is happening here is here, this is like there are 10 numbers here. So the input X that we were providing was not a single image for all the functions before. We were providing all the inputs as all the images as one input. So maybe we can add one more dimension and then run this to see what the prediction is. Okay, so now the predicted label and actual label are matching. And now we can also see how the image actually looks like. Okay, so this is 4, predicted is 4, actual label is 4, and image is also looking like a 4. And then now we can put some random indices like 10, predicted is 6, actual is 6, validation index is 10. How many? I think there are 8,000 something, 8,400. So we can go up to 8,400, any random index like 1,000. I'm sure some of them will be wrong because accuracy is only 87%. So 13% of the cases you will get mistakes. But overall, our prediction is working really, really nicely, predicted label and actual label. And this is in validation data. This data was not part of training, completely new data, and predictions are happening. And if we want now to get an overall test accuracy, I mean, validation accuracy, what we need is get predictions of, basically, we should have a 2 val for all the, a 2 val equal to forward propagation of x val, and get predictions. And what should we do? There is one more function that we have defined, that is get accuracy of predictions comma y. So get accuracy of get predictions comma y val. Y val is the index. So then hopefully this should be validation accuracy equal to accuracy. We just need to print this variable. Hopefully this should work. Okay, so training accuracy is 0.871 and validation accuracy is 0.874. This is amazing. We have literally built this neural network completely from scratch. I will be sharing the code with you, this Google Colab notebook I'll be sharing with you. I will be also sharing the Google Drive link to this particular train.csv dataset so that you don't have to go through the pain of downloading it and again uploading it to your drive. So you can directly put this particular dataset in your drive and you can start using. But I highly recommend you to do everything from scratch so that you will learn, and maybe it will take you some time to reach the level where you are very comfortable implementing this whole thing from scratch. Of course, it took me some time to figure out some mistakes that I was making because I had already written this piece of code before, like over here in this V2, which you can see, and I had tested it. I made a lot of mistakes initially while writing, and now I know where all to pay attention to, but you will not know just by watching this video. You have to implement it yourself to see that. The video has become slightly longer than I expected, but I think it's better to go slow and go through all the concepts one by one. So the first half of the video, we covered mathematics behind neural network, constructing a neural network for this image classification task. And the second half was about implementing it completely from scratch. We do have a built neural network from scratch course with assignments and various other modules plus handwritten notebooks, etc. So I'll be sharing the link to that particular course in the description. Just check it out. If you're interested, you can enroll in that. You will also be getting a certificate at the end of it. It's a completely self-paced course. So I'll be sharing the link to that also in the description. But thank you so much for listening. Thank you if you have tried implementing this yourself and if you found it very useful. We'll meet again in another video, but really appreciate you for spending this much time along with me learning this completely from scratch. Although I completely understand that it's not needed in today's world, you can literally execute all of this in few lines of code by importing packages. But then what's the fun in that? Where is the learning happening in that, right? You have to understand the basic mathematics or the foundation level mathematics that is happening underneath the curtains. And I hope this video sheds some light into that. So thank you so much. We'll meet again in another video. Take care until then. Bye.